The BoxCox transformation and the YeoJohnson transformation are two very useful transformations that can induce normality into your data. You can see from this graph of the average income variable, both of these charts represent the same information. The average income on the left hand side is highly skewed, whereas after applying a BoxCox transformation on average income, it is more normal or more Gaussian like behavior. It exhibits a more Gaussian like behavior. The same is true for Yeo-Johnson transformation as well. This is of great significance because a variable fitting a model on a transformed variable, especially BoxCox and Yeo-Johnson transformed variable, tend to perform better in terms of performance such as MAPE and mean squared error compared to the raw variable itself. From a utility standpoint, the difference between the BoxCox transformation and Yeo-Johnson transformation is you can apply the BoxCox transformation only on variables that contain positive values. If your variable contains negative value, you cannot use BoxCox. Whereas Yeo-Johnson transformation, you can apply on variables that have negative values also. Of course, you can apply this on positive valued variables as well. Now let's look at the formula. What you see here is the formula for both BoxCox as well as Yeo-Johnson. There are two versions of formula for BoxCox transformation. One has only one parameter. Here the parameter is the lambda. The second version has two parameters, lambda 1 and lambda 2. Now how lambda value is calculated is taken care by the software itself. Ideally, the lambda that provides the best normal distribution is normally chosen, and that value is computed using an optimization algorithm. Now how to read this formula is for a lambda value that is not equal to 0, the top formula would apply. If lambda value equals to 0, then you just take a natural log of each observation in your y variable. In a similar way, you can interpret the formulas for two parameter BoxCox as well as Yeo-Johnson. The formulas are not so important, but the utility of applying this transformation is very important. Let's see how to implement BoxCox transformation. We are working with the California school dataset. I have imported the dataset from this location and split the data into training and test data. Both Yeo-Johnson as well as BoxCox transformation is present in the caret package. To apply Yeo-Johnson transformation, caret package has a function called preprocess. The first P is small case, the second P is capital case. The first argument of preprocess is the variable that you want to do the Yeo-Johnson transform, but it should be passed in as a data frame. That is why I have explicitly included drop equal to false. So if you run this, the result will be in the form of a data frame. You can see that there is only one column here. So this is just the average income but present as a data frame. If you don't include that argument drop equal to false, the result will be present as a numeric vector. That is the reason we are having drop equal to false. And set method equal to Yeo-Johnson. Run this. Yeo-Johnson model will be built. This displays the lambda parameter as well. Right? You can just substitute this lambda parameter into Yeo-Johnson formula and get the resulting values. And that's what happens when you apply predict function on the Yeo-Johnson model. I'm going to apply it on the same column. Now if you look at df train, this has a new column called average income yj. In a similar fashion, you can implement BoxCox transformation, but you have a function directly for that. In caret, it provides BoxCox trans function. Just pass your column into that and apply predict. You will get the BoxCox transformed version of that variable. Now we have computed the transforms. Let's visualize them. This is the histogram and density for the raw income variable. Let's do it for BoxCox. This is more normal like, right? Likewise, if you do it for average income, this is also normal like, except that it has more values concentrated in the center. So the density has increased near the mean region. Now, a very useful aspect of BoxCox transformation is it often helps to improve the model fit. Instead of using the raw variable, if you use the BoxCox transformed or YeoJohnson transformed variable, there's a high chance that the fit of the model improves. When I say fit improves, it improves the R square, adjusted R square, and optionally the test MAP also. But this is not a guaranteed thing. This is a generally observed phenomenon that happens. Apart from this, it also helps to overcome the problem of heteroscedasticity. One of the assumptions of linear regression is the variance in error is the same, is constant. If heteroscedasticity happens, then applying a BoxCox transformation on your y variable followed by the x variables could be a possible option to overcome heteroscedasticity. Again, it is not a guaranteed solution.